Yeah, hello everyone. Um, we'll continue from where we left last time. We were here, and we are in the chapter of convex functions, and we are doing some practice on how to prove convexity. And this was the example where we left last time, which is log determinant. And it says that f of x is log of determinant of x, where x is a positive definite. And we have to prove that fx is a convex function. Here x is a matrix. Okay, so it's a matrix function because we talk about determinant for matrices. So here x is in R n by n, and so it's a square matrix because determinant will make sense for square matrix, and it's a positive definite. Okay, and it's a symmetric and positive definite. And x is in Sn plus. Okay, so this means symmetric and positive definite. Okay, so to prove this, we will use the result that we have proved before. So f from Rn to Rn, Rn to R is convex if and only if f restricted on a arbitrary line in Rn is convex. So this is the result that we are going to use. A multidimensional function is convex if and only if it is restricted, if f restricted on arbitrary line in Rn is convex. Okay, so this will be the one that we are going to use here. So let us consider some line in the domain. Okay, so this will be the line that we want. So it's a function of matrices, right? So the function f is defined so that let us say this is the function f, and this is the domain where a function takes the values. So in the domain there are matrices like Z and V. Okay, so these are the points in the domain, and then we consider an arbitrary line, right? So it is an arbitrary line because Z and V are arbitrary. So this is like arbitrary line joining 2 points. Okay, so this will be the line Z plus TV, and so if it whenever it's restricted on a line, it's convex, right? So let us see, in this case, it's like t is between 0 and 1. So this line starts from Z and it ends at V. Okay. And so it's like any arbitrary line. Okay. So in this case, let us say this is the line. And if we can prove that for any 2 point and then the line joining them, if the function is convex. So if for these values, the function might be taking, let us say these values. Okay, let us say some values it's taking. So this is the fz, and this value is fv. Okay, so this is the height of the function here, and this is the value taken by the function here. So this is the line joining these 2 points, right? So so if we can prove that the function restricted on this, which in this case, this will be the GT line. Okay, this is the GT. So G of 0 will be FZ, and G of 1, okay, will be Z plus TV. Okay, let's see. Yeah, I mean the way our line is denoted is like you go up to Z plus V. Okay. So at 1 you will be at Z plus V actually. Okay. So so it could be like somewhere here actually. Okay, it could be somewhere here, Z plus V. If I do the vector addition, then it would be somewhere here. Okay, so I wonder this is correct. Should I take a convex? The original statement. The original statement was line joining them, or is like any arbitrary line. So yeah, I will check this again as I go along. Okay, so consider this line, but anyhow, this is some line. Okay, and if we consider this, then what is GT, right? So what
Hello,
is
sir.
GT? Yes.
Say the original statement was a function is convex if and only if it is convex when restricted to any line that intersects its domain.
Yeah, any line that intersects its domain. Yes. Okay. So in that case, we don't violate anything here because this is some line that intersects its domain. Why? Because so why this is any line that intersects the domain? It's like the domain is the set of so domain of F is this is Sn plus. Okay, so it's like positive definite symmetric n by n positive definite function. These are the domain where the function is defined. So we have to take any arbitrary line that intersects this. So this will be in the domain because so the claim is that Z plus TV is in the domain of F. So to prove to do that, we have to prove that this is symmetric and positive definite. But this is true because so Z and V are both in this. Okay, and then if I sum this, then this sum is also symmetric and positive definite. So this implies that Z plus TV is also symmetric and positive definite, right? So I can check like if this X transpose Z plus TV, I have to check. So this will be X transpose ZX plus T times X transpose VX, right? So since Z is positive definite, okay, since Z is positive definite, this is greater than 0, and this is positive definite, so this is greater than 0, and T is a number between 0 and 1. Okay, so this is at least greater than equal to 0. So whole thing is greater than 0. Okay, I mean, so hence this is positive definite. Okay, and it is symmetric is very clear because Z and V are individually symmetric. So sum of symmetric matrices remains symmetric. So it is a valid line, and this line is in the domain, and it's arbitrary because Z and V I have chosen is arbitrary. So with a proper choice of Z and V, I can create any arbitrary line that I wish in this domain. So this is a arbitrary line. Okay, nothing special about this. So we have to take arbitrary line because the theorem demands that. Okay, to claim that F is completely overall it's concave, right? In other words, minus F of X is convex. So that's what we are supposed to prove. Now I have written a few things here that will help. So GT is F of G plus TV, which is log of determinant of Z plus TV. So that's what we have written here. Now we have done some manipulations here. So what is that? We have taken square root of Z common from the both side, and square root exists. Okay, why square root exists? Because it's symmetric and positive definite. Okay, so what is the fact here? So square root of a matrix exists. Okay, so if a matrix A is in Sn plus, then square root of A exists. So this square root of the matrix exists. Okay, so this is the result here, because in general square root may not exist. Okay, I mean, in case of real number, you know that that square root exists if x greater than 0, then square root of x exists in real. Okay, and if x is less than 0, then x square root number does not exist in real. Okay, so if x greater than 0, then square root of x is still a real number. But if x is less than 0, then it is no longer real number. It will become complex number. Okay, so then we say it doesn't exist in real because it's complex. That's, you need another number system for that. And here same analogy holds. So in the matrices, you need symmetric and positive definiteness, and then you can take a square root of that. Okay, so so the square root exists. Okay, because Z is symmetric and positive definite. So I take square root common from both sides. If I do that, then if I multiply this back, you get back this. That's what. So if I multiply Z half and Z half, then I get back Z here. Okay, and then here if I multiply by Z half and Z minus half, then I get back identity. And here if I multiply Z half and Z minus half, again I get back identity. So remaining term that I get will be just V, TV. TV will be left out. So this is correct. And next thing what we are trying to do is apply the determinant formula. So determinant of AB is determinant of A times determinant of B. So another fact from linear algebra that we want is determinant of AB is determinant of A. Yeah. Yeah, that's correct. Okay. So determinant of A will be, AB will be determinant of A times determinant of B. Correct. And so what do we do here? So how should we use this determinant here, right? So if I multiply the determinant, this will be determinant of this, and then this will be determinant of this times determinant of this, right? So so I can put them together. So this determinant I can put them together, and then this determinant will be the one that will be left out. So this step I can clarify here. So this is like log of determinant of so let us keep this here. Okay, so this is like determinant of Z half, and then determinant of this I plus T Z minus half V Z minus half, and then determinant of Z half. Okay, and this will be so this and this I can combine. So this will be log of let me write the first term. So determinant of I plus T Z minus half V Z minus half is the first term, and then these two terms combine, and this become just determinant of Z. You get back the determinant of Z, and this is the logarithm. So this will become the sum. Okay, so log of x y is log x plus log y, right? So this will be log of determinant of I plus T Z minus half V Z half. Okay, and plus a log of determinant of Z. Okay, so after this, then we wrote this step here. Okay, so this step then goes here. So this is log determinant Z is okay. And this part we have expanded here. The reason, the way we have expanded is that we assume that the eigenvalues of these, okay, the eigenvalues of these are lambda I. Okay, so if the eigenvalue of these are lambda I, then the eigenvalue of identity plus t will be 1 plus t times lambda I. Okay, and determinant is the product of the eigenvalues. So the eigenvalues of these are 1 plus t lambda 1, 1 plus t lambda 2, and so on. And determinant of that matrix will be the product of the eigenvalues. And then the product will split into the sum because of the log. Okay, so that's what is happening here, right? So lambda 1, lambda 2, lambda n are the eigenvalues of this. Yeah, this z half. So if you go back here, okay, so let me do this. So let lambda I be eigenvalues of this guy. Okay, so the eigenvalues of I plus this will be 1 plus yeah, so eigenvalues of these will be 1 plus, yeah, so this implies eigenvalues, excuse me, so eigenvalues of this guy will be 1 plus t lambda I. Okay, this guy of this guy will be this. And then if I take the log of this, I mean the determinant of this, so this implies that the determinant of I plus t z minus half v z minus half is product of the eigenvalues. So I equals to 1 to n, and these eigenvalues are 1 plus t lambda I. And then if I do a log of this, okay, so which is the log of here, so log of these guys will be sum of the 1 plus t lambda I. Okay, so I equal 1 to n. So that's what is written here in a compact form. Right. So what is the motivation here? Motivation here is to reduce these complicated expressions into some simple sum of some single variable function. So you can see this as a simple function with parameter t. It's a sum over n terms like that. So it will be easier to check convexity of GT. Remember, our goal is to this is the function restricted. This is the f, the small f, restricted on a line. And we see this restriction as some other function GT, and we have to prove that GT is convex. So we simplified this so that it becomes sum of some simple functions, which in this case is log of 1 plus t lambda I, which is a simple function for us to analyze. So we can do g prime t now. So we differentiate this with respect to t because we have to prove that g is convex with as a function of t is convex. So we take the first derivative. So this will be 1 by 1 plus t lambda I. And then by the chain rule, so inside you have to do the derivative. So derivative of this with lambda I will be just lambda I. I mean derivative of this with t will be just lambda I. So this is the derivative we know, and summation will keep will be there. And derivative of this with respect to t will be 0 because there is no t dependence here. So this term goes away after taking the derivative. So at the end, this is what we get. And we can take one more derivative with respect to t. So we took one more derivative here, and then we get this. Okay, so if we take derivative with respect to t, then this will be like minus 1 by 1 plus t lambda I squared, and then the derivative of the inside term, which will again be one more lambda I. So there will be 2 lambda i's. So that will become square. Okay, so now the question is like we want to use the second derivative test. So want to use second derivative test for GT. Okay, for GT. So now the question is like, is this necessarily for concavity? For concavity, what do we need? A function is concave if f is concave if the double derivative is less than 0. Okay, for convex it's greater than 0, greater than or equal to 0, and concave it's less than or equal to 0. Okay, so that's what we have to prove. Now, is this less than equal to 0? So is this guy less than equal to 0? It is, because this is positive. Okay, so this term is like greater than equal to 0, and this term is also greater than equal to 0. So overall, this is greater than equal to 0, and then you are putting a minus. So this overall becomes less than equal to 0. Okay, so this is how we prove that second derivative test tells us that G is concave. In other words, the function restricted on the arbitrary line, f restricted on the arbitrary line, is concave. And since the line is arbitrary, we conclude from the previous result that that f is a concave function. Okay, so this is what we this is how we prove this in this case. So now what I will describe is something called epigraph. So epigraph is formally defined as follows. So graph of a function f. First of all, I define a graph.
Hello, sir.
Yes.
Yeah, sir. So here you considered a random line from your domain and proved the convexity on that line.
Yes.
So since it is since we proved that g of t is concave, from that we are concluding that f of t is also concave, since our that the line is an arbitrary line, right?
Yes.
Yes, sir.
Yeah,
Okay,
that's
sir.
correct. Okay. Yeah, so let us go to the epigraph. And so first of all, we recall what is a graph. So graph of a function is the pair x comma f of x, where x is in the domain of f. Okay, so this is the way graph is defined. Okay, so so for a given function, let us say fx is, let us say, x squared, then we know that the graph is like a parabola, and so the points that we have here, so this is the x that we have, and this is the fx that we get. So these points are denoted by x fx, right? So this is how we collect all those points, and that denotes the graph. So this is the x fx points that we collect, that denotes the graph, and this should be only for the points in the domain, obviously, where the function is defined. Now epigraph of a function f from Rn to R is defined as follows. So it's like x and then t now, okay, and x is in the domain of f, and this is the condition that is to be satisfied, and set of all points t which are above the fx value. So these points, if you see, these are like, let us say, x1 fx1. Okay, these points are like x2 comma fx2. Okay, and the domain here is like, this is where I have x1, this is where I have x2, and so on. So these points are like this, and here we have put t here, right? So it's like, it is saying like set of all xt where t is greater than equal to fx. So I have to collect all those xt where t is greater than equal to fx. So in other words, I have to collect all those points. So this is still the point, let us say x1 t, where t is greater than equal to fx1. Okay, so the t is greater than, so this is the point that I have to consider. Here also, if I consider this, then this is also the point where t is greater than equal to fx1. So all these points will be covered. Similarly, you take another x, and let us say let us say here x2. Then you have to take x2 comma t, where t is greater than equal to fx2, and then t is greater than equal to fx2 for another t. Okay, so this is like some t here, right? So this is like x2 comma, let us say this is like t2. Okay, and then you have to take points like x2 comma t3, such that all are above fx2, and this you have to do it for all x in the domain of f. Okay, so if we do this, then we get points like this, and that will form a set. Okay, so that will form a set which is called AP of f. Graph is also a set. Okay, so this is called epigraph. So to summarize, all the points above the function, all the points above the function forms an epigraph. It's a set. Okay, set of all points above the function. So that's epigraph. And hypograph, similarly, we can define hypograph as the points below the function. Okay, so hypograph will be these guys below fx. Okay, so these are like hypograph. Okay, so these are hypograph. So this is the result. A function is convex if and only if its epigraph is convex. Okay, so this function would have been convex if the epigraph, this set as a set, it's convex. So there are two things we are relating. This we are saying the function is convex, and this we are saying the set is convex. So from here to here we are saying convexity of a function, and here we are saying convexity of a set. Okay, so you see how convexity of a function is now equivalent to convexity of a epigraph of the function. Okay, so this is how convex set. Remember, convex set definition was like you take 2 points and the line joining the 2 points is in the set. Whereas definition of convex function was that you take 2 points on the graph of the function, then the line joining the 2 points on the graph is always above the function values between those 2 points. Okay, so that's how these two ideas get connected. Okay, so in this case, for this function, what do you think? Is this a is the epigraph a convex function in this convex set? So what do you think? Is epigraph a convex set for this example?
No, sir. No.
Yeah, no, because I can take arbitrary points like this point, and then the line joining them is not completely inside epigraph. Okay, so this line is not inside AP of f. Okay, this implies f is not convex function. Okay, so this is how we can relate, and actually one can prove this fact. Okay, so if f is convex, then epigraph is a convex set. Okay, if f is convex, then epigraph convex set, and if epigraph is convex, then f is a convex function. So it's if and only if case here. Okay, so I may leave this proof for you to like. Yeah. Yes.
So the line joining is greater than the function values. Itself explains the fact that the line joining implies in the set the line is joining, right? If we consider it as epigraph.
Yes. Yes, exactly. That is the intuition. Yeah, your intuition is correct. Yeah. So if the line, so what you said is like if the line joining this is above the function values or the graph of the function, then this indeed also means that the line must be in the epigraph by the definition of the epigraph. because these points are exactly the points x comma t for which these are greater than fx values here. So that's correct. The intuition is right. So you can try to prove this explicitly. I'm not going to do this. This will be easy proof. I don't see any complications. So I let this as an exercise for you to do. Okay. So how to prove this fact. Okay. Okay. So and similarly we can so this will be concave. So a similar argument we can make for concave. In the concave case, we have to go for the hypograph, which will be this guy. Okay. So a function is concave. Oh, okay. 1 second. Is this? Yeah, I think this will be still convex, right? So a function is concave if and only if its hypograph is convex. Okay, so that is correct. A function is concave if and hypograph is convex. So a concave function will look like this. So the hypograph is this. Okay, so a function will be concave if the hypograph is convex. Okay, so that's correct. So you can prove these facts. Okay, I leave this up to you. We have done a lot of examples on proving convexity of sets and functions and so on. Now you should do this. Okay. So there is a scratch space for this proof, but I will ignore this. Okay. So now what I will do is something called Jansen's inequality. So J is silent here because it's a Dutch name, Jansen. So in Jansen, J is silent. J is silent in Dutch. Okay. So Jansen's inequality, what does it say? Given f from Rn to R, yeah, so given f from Rn to R, if this is satisfied, okay, if this is satisfied, then we say that the Jansen's inequality is satisfied. Okay, and important thing to note here is there is like it's for all theta in R. Okay, so it's like all theta in R and x and y in Rn. So this is the Jansen's inequality. And it can be extended to convex combinations as well. So it doesn't stop us to also put restriction on theta, because here it's like all possible theta. So this is just a special case where theta does sum to 1. Okay, so we can extend this to convex combinations also. So theta x1 plus theta x2. So it's like multiple components are here. In this case, we had only x and y. So it's like, but here we can do it for a lot of sums here. So this is the Jansen's inequality, and we will in the next few slides, we will see some examples and applications of this. Jansen's inequality can be written for integrals. So if we have some function px which is greater than or equal to 0, then integral of px x dx will be less than or equal to integral of fx fx px. Yes. Yeah, that's correct, right? Okay, so if px is greater than or equal to 0, then yeah, so here you have f. Okay, so f of integral of px ax dx will be less than or equal to fx integral of fx px. Okay, so that's correct. Okay, so this how is this coming? You go from discrete case to continuous case by so the summation is replaced by the integral, and the weights theta I are replaced by these px. Okay, so the weights are replaced by the px, and here sum is replaced by the integral, which is this integral, and inside you have fx and then the weights which are theta i's, right? So which are these px? These are the weights, right? Okay, so this is the Jansen's inequality for integral, and it can be also used to write it for expectation. So in other words, we know that in the probability, this is the expectation of x. Okay, assuming that this is the PDF of the random variable x. So if px is the probability density function PDF of continuous random variable x, then the expectation of x, okay, or x is defined as integral of px x dx, right? So if you recall this from the probability, then this is what we can replace this, assuming that this px is a probability density function, right? So the way it is defined here, actually, it satisfies all the criteria of probability density function. So this px is greater than or equal to 0, and the integral of px dx is 1. So that is exactly the requirement for px to be a probability density function. So I could have written this also as f of e of x, right? And then this is less than or equal to, and this is the expectation of f of x, right? So this is nothing but expectation of f of x, right? So expectation in general is defined. So expectation of a function of a random variable, right? So let us say this is the function of a random variable. Then this is integral of f of x times the PDF of the probability density function of x, which is px and dx, right? So this is how the expectation of f of x is defined. So this is what we have written here. So we can interpret this inequality: if x is a random variable, then we can also write it in this form. Okay, so this is how Jansen's inequality look like. If x happens to be a probability, it happens to be a random variable. Okay, so what is Jansen's original inequality? Original inequality of Jansen was this, okay, where he said that f of x plus y by 2 is less than or equal to fx plus fy by 2. So what Jansen says is that if a function is continuous, and then Jansen's original inequality becomes the necessary and sufficient condition for convexity. So if f happens to be continuous, and if the function satisfies this inequality, then that will be the necessary and sufficient condition for convexity. Okay, so f continuous plus f satisfies, okay, so plus or and, okay, so f satisfies Jansen's inequality. So this implies and implied by f is convex. In other words, if f is convex, then this holds. But this way is easy, right? So if f is convex, this implies Jansen's inequality is easy, because if f is convex, then what we know is that f of theta x plus 1 minus theta y is less than or equal to theta f of x plus 1 minus theta f of y. And this is true. This is true for like all theta between 0 and 1, but then in particular I can choose theta to be half. Then this immediately implies star. So this immediately implies star for theta equals to half. Okay, so this way is okay, but why should the forward implication hold? So f is continuous and f satisfies Jansen inequality. Prove that this will hold for all theta between 0 and 1. Okay, so again, this is I'm not going to do this now, because this I will skip it again. Okay, but what is to remember is like This is a necessary and sufficient condition for convexity. So this is yet another way you may prove that the function is convex. And this may be a bit easier sometimes to prove because there is no theta needed anymore. It's just, or in other words, theta is just fixed to be half. And you also have to assume that the function should be continuous. So that's the requirement here. Okay. So, okay. So, so these are the results that we find from his paper where he described his results, which we see this in this form. Okay, so he has written this in this form here. So it's written in French, and he says that, so how Jensen got motivated? Well, he got motivated when he was trying to prove some inequality. For instance, one inequality that we know is like geometric mean is less than equal to arithmetic mean. Okay, so this is the result, and these are this follow also for more number of generalized arithmetic mean and geometric mean. Is here it's like geometric mean of 2 numbers, but here you have for 4 numbers. So when he was studying this inequality, then he thought, what are the necessary conditions, how we can generalize the idea so that variety of inequalities can be proved. And in particular, AMGM inequality will become a special case of that. So it turns out that Jensen's inequality can be used to prove AMGM inequality. Okay, so consider the AMGM inequality, and so how do we prove this inequality? Let us say like we want to use Jensen's inequality, right? So Jensen's inequality requires you to provide a function, right? So which is the function that we are supposed to choose? And that function satisfies the so that function is like convex. Okay, so if the function is convex, then obviously it satisfies the Jensen's inequality, because we have seen because we have seen that convexity is like if and only if the function is convex and satisfies the Jensen's inequality. Okay, so what do we have here? Like, so we can choose some function, right? So choose the function f of x to be minus log x. Okay, so this function is convex. Okay, so this function is convex, and so we can check that this function is convex. Okay, but you can take a double derivative test, and that's easy. So I leave this up to you why it is convex. Now we will apply Jensen's inequality because this is convex. So this implies that it satisfies Jensen's inequality. This implies f satisfies Jensen's inequality. So with theta equals to half, right? So with theta equals to half, we choose theta equals to half. It is our choice. So this is like minus log x. Not okay. So let me. Okay. So the Jensen's inequality, the special case I'm saying, okay, because Jensen inequality is general, right? Jensen inequality is general. Okay, so this is the general case of Jensen inequality. This is the special case of Jensen's inequality. So we are trying to apply the special case in the logarithm case. So what this says is like f of x plus y by 2 is less than or equal to fx plus fy by 2. In our case, x and y are a and b. So f of a plus b by 2 is less than or equal to half of f of a plus f of b. Okay. So so this is the Jensen's inequality. So the function is convex, it's continuous. So I am So this function is convex, so it satisfies the Jansen's inequality with theta equals to half, and then that's what we have written here. And then this will be minus log of f is log, right? So it's a plus b by 2, and then this is less than equal to minus log a minus log b by 2. Now remember, our goal is to prove this inequality, right? So taking exponent on both sides, taking exponent on both sides. Okay, so if we take exponent on both sides, so what will happen, right? So exponent of the logarithm and so on, right? So what should we do now?
Sir, RHS will be minus log AB, right?
So this is like minus log A and minus log B by 2, right?
Yeah, you can take minus common.
Yeah, so this is like, yeah. So this is like you can take minus common and minus log AB. Okay, and then you can also take this half and make this square root, right?
Now multiplying both sides by minus will reverse the inequality.
Yeah, so multiplying both sides by minus will reverse the inequality, and then so we remove this, and then we get greater than equal to, and then we take the exponent. So exponent and log will cancel, so this implies a plus b by 2 is greater than equal to square root of ab. Okay, so that's how we saw an application of Jansen's inequality. So so that's what I did this already. Now we can prove another result. It's something called Holder's inequality. So what is Holder's inequality? Let us say some p, which is greater than 1, and then 1 by p plus 1 by q is equal to 1, and x and y are in Rn. Then Holder's inequality says, so the Holder inequality says is sum of the xi yi is less than equal to to the pth power, sum of the pth power of xi to the power p, and sum of the qth power of absolute value of yi to the power 1 by q. Okay, so this will look a bit too much, but what is the special case of Holder's inequality? Do you recall we have used some inequality before, right?
Cauchy-Schwarz.
Cauchy-Schwarz, right? So this is special case. Special case is Cauchy-Schwarz. So in Cauchy-Schwarz, to get Cauchy-Schwarz, what are the changes I have to do here? What are the parameters I should choose? P is
equal to 2.
P equals to 2 and Q equals to?
Q will be 2, right, sir?
Q is also 2. Yes. So both P and Q are 2. So if we see this, then it is indeed like X transpose Y is less than equal to norm X to norm Y. Okay. So this was indeed the Cauchy-Schwarz inequality, right? So this was like sum of xi square is sum of yi squared and squared. Yes, and here also we have squared. Okay, so for p equals to 2, q equals to 2. So this is what is Cauchy-Schwarz inequality, and
sir, I have a doubt. In the formula, it's written x to the power xi to the mod p to the power p and the whole sum to the power p. So it will be 1 by p or p exactly?
Yeah, there seems to be some error here, right? 1 by p, yes. And 1 by p is actually, these are square roots, right? Yeah. So this will be square root, right? Yeah, that's correct. Yeah. So this will be square root of xi squared and yi squared, which is actually nothing but the norm 2 norm. So what I wrote was actually correct. So this 2 norm of x and 2 norm of y. Yeah, there was an error here. So it will be 1 by p. Okay. Yeah, then it will be Cauchy-Schwarz. So to prove Holder's inequality, again we choose the function f of x is minus log x, and which we know is a convex, because log x is concave, so minus of that will be convex. Okay, so for a general theta, we want to use this inequality now. So by convexity of minus log x and Jensen's inequality applied on general theta, like here we did it for a half and b half is less than equal to a plus b by 2. But if we choose the general theta, so if we choose general theta, then this would have looked like theta, a to the theta b to the 1 minus theta is less than equal to theta a plus 1 minus theta b. In the previous proof that we did here, right? So here we choose we have chosen theta to be half, but if we choose theta to be something arbitrary, right, and then the sum, so theta that we choose is like theta and then 1 minus theta. There are like 2 theta we choose. Then if we apply the Jensen's inequality, so Jensen's inequality in this case will be, so let us say theta 1 will be this and theta 2 will be this. So using Jensen's general inequality, it will be f of theta 1a plus theta 2b is less than equal to theta 1 fa plus theta 2 fb. So this will be the general variant of the Jensen's inequality. And so theta 1 in our case is theta. So this will be like minus log of theta a plus 1 minus theta b, okay, is less than equal to minus theta 1 log a minus so let us say theta 1 was theta and then minus 1 minus theta log b. Okay, so and then we take the exponent, we multiply both sides by minus 1, and then we take the exponent, then this will go away, and what we will be left with is theta a plus 1 minus theta b yeah, so if we subtract, so it will be log of theta a plus 1 minus theta b, and inequality changes because multiplied by minus 1, so theta log a plus 1 minus theta log b. Okay, and then if we take the exponent, and here this exponent will make it a product. Okay, so this will be, this right hand side will be log of a to be theta times b to the 1 minus theta, and now we will take the exponent and we get back the result. So that's what we have written here. This result we get, okay, by taking a general theta in the Jensen. Now once we have this, and we choose simply choose a to be this and b to be this. Okay, and theta to be 1 over p. Okay, so if we choose, if we fix a, b, and theta to be this, we immediately get the Holder's inequality. Okay, so So if we put this in the theta, a to the theta and b to the 1 minus theta, right? So this is a to the theta. Okay, so let's see. So 1 by p, and then yeah, so a to the theta and b to the 1 minus theta. So let us do this with these choices that we have, right? So a to the theta is 1 over p, right? So a to the theta and b to the 1 minus theta, right? So this is b to the 1 minus theta. So this will be like this to the theta, okay? So xi p by summation xj p, okay? And this is to the theta, and this is yi q by summation yj q, and this is like 1 minus theta, and this should be less than equal to theta a plus 1 minus theta b, right? So theta in our case is like, let us put this p, right? So this is like theta is 1 over p. So, and this is like 1 over p, so 1 minus 1 over p, so like p minus 1 by p, like p minus 1 by p, and this is less than equal to theta a plus 1 minus theta b. So theta a is like 1 theta of a, right? Yeah. So is it necessary to write all this? Let's say theta a plus 1 minus theta, so it's p minus 1 by p. Okay. So what do we have now? So does it boil down to this? So let's see.
Hello, sir.
Sir,
if you take summation on both sides, in the right hand side, already denominator is summation. So we don't get any change. The numerator will be exactly same as denominator. So both get cancelled off, and we will get 1 by p plus 1 by q. That's it.
Yeah.
And 1 by p plus 1 by q is 1 we already proved. So the LHS denominator will go to the RHS side, and that's the proof, right?
Yeah. Yeah, so yeah, that's the, so we have 1 by p, and then like, yeah, 1 by q. So 1 by q, this guy is actually 1 by q, right? It's like 1 by q. Yeah, so I think what we are missing here is this, guys, 1 by p and 1 by q. Okay, these are the typos here, and this is what we have. And then if we sum it, okay, so if we sum the terms on both sides, then we will get back the original inequality. So original inequality, the original inequality gives us what? Okay, so if we sum the terms, right? So in the left hand side, what do we have? Right, so on the left hand side, if we see here, if we have xi to the power p and 1 by p, and yi to the power q and 1 by q. Okay, so this will be just xi yi on the numerator. Okay, and then the denominator will be 1 over p and then 1 over q of this. Okay, so the numerator will be like xi and then yi. Okay, and if we are also summing it up, so this will be I equals 1 to n, and we are also summing these terms. Okay, so let me still write this term. So xj to the p, and this is like 1 over p. Okay, so we distribute 1 over p on numerator and denominator. That's what we did, and then this will be also, this term will also be there, and yi is already absorbed here. So this is like summation yi q and 1 over q. So this is what happens for this term. Okay, and then we are also summing things on here, but these guys will sum to 1. Okay, if you sum these guys, up to for j equals to 1 to n and so on, so sum of these guys will be 1. Okay, so if I sum this xi p by xj p 1 by p plus 1 by q summation yi by yj q. Okay, so if we sum this, then this summation will be 1 here. So this will boil down to 1. Okay, and because there is no I dependence here, because this is already summed up, so there is no I dependence here. We are summing over the I. Okay, so this sum is over I, whereas this sum is over j. So these guys will also turn out to be 1. So we have 1 by p plus 1 by q, which is 1. Okay, so overall here we will have this guy is less than or equal to 1. Okay, so overall this guy will have less than equal to 1, and then we will move these denominator on the right hand side. Okay, because these are sum over j. Okay, so if we write it down here, so we have sum of xi yi by sum over xj sum over yj. Okay, and these are powers p, and then this is 1 by p, and this was 1 by q, right? So that is like q here, and this is like less than equal to 1. Okay, so far this is what we have, but then we move this there, right? So this implies xi yi, because there is no I term dependence here, so this is like a constant, so it can be moved that way. One over p, and then here also we have yj, j, the summation is over j, and then q, and then 1 over q. So this is the Holder's inequality, right? So what we have seen is that we started with a function which is convex, and then the Holder's inequality holds for this function, and then we use this inequality with a proper choice of a and b and theta to prove the Holder's inequality. Okay, so these are some applications of Holder's inequality. Now, what are the operations that preserve convexity? So for instance, if I do a non-negative weighted sum, so if f1, f2, fn are convex, and if I do a weighted sum like this, so w1, f1, where w1 are the weights, wm, fm, and so on. So then their weighted sum is convex. If the individual f is convex, then the weighted sum is also convex, and provided the domain is the domain of intersection. That's how the sum of the function will be defined. If the domain of f is the intersection of the domain of all these f. Okay, so this is again a straightforward thing to do. So I leave this up to you to prove that weighted sum of convex function is convex. Another thing is composition with affine map. Okay, so if a function from f from Rn to R is there, and A is a matrix n by n, and B is in Rn, then if you define a function gx, which is a function of Ax plus B, then if f is convex, then G is also convex. Okay, so if I do an affine map via a convex, if I do an if I do an affine transform of the convex function, then it remains convex. So in other words, like if I'm given an x in some domain and if I've done an affine transform which is Ax plus B, then the function still remains convex. Okay, if f of s was convex, then f of Ax plus B also remains convex. Okay, so affine transformations of the domain doesn't change the convexity of the function. Okay, and obviously, like Ax plus B must be in the domain. It must be a well-defined. It must be those points where domain is still defined. Okay, so that's what this result says. Okay, so affine transform doesn't change the convexity of a function. Okay, so what do we like? How would you prove these results, right? Yeah, so if f is convex, then G is also convex. So we need to prove that G is convex. So to prove G is convex, so we have to take, let us say, theta G of x plus 1 minus theta G of y. So this is how much? Theta G of x is theta of f of Ax plus B, right? So this theta of f of Ax plus B plus 1 minus theta of f of Ay plus B.
Plus I.
Yes?
Sir, isn't it the same proof which we followed for saying that if a line is convex, then the whole function is convex, like an arbitrary line? Isn't this the same with that?
I mean, here we are not talking about restriction, right? We are that result is a little bit different. There you are talking about restriction of a line, but here it's a translation of the domain itself. We are translating the domain. So remember where, let us say this is my domain, and then I did a affine transform. So it will get maybe rotated and then translated like this. So this was my point, let us say some domain D, and then I did Ax plus B, then I get this. So it can essentially get rotated and then translated. So the question is like now if the function was defined here, fx, now in this new set of points D prime, okay, so let us say D prime in the new domain, whether it will retain the convexity. So that's what this result is saying. But what the previous result was saying was we were never doing the translation of the domain. We were saying if f is convex, then it's convex on any arbitrary line in the domain. Okay, but here what we are saying is a little bit different. We are saying that we are going to something else. We have rotated or translated our domain points, and then we move to somewhere else, and then we are asking whether it's convex or not. So it's a slightly different thing. Okay, it's a slightly different. Yeah. So so this is but the function f is a convex function. So theta of f of, let us say, u plus v, right? So theta of f of u plus 1 minus theta of f of b will be greater than equal to, right, greater than equal to f of theta u plus 1 minus theta v, right? So so this is what we have. Now remember, what we have to prove is that the g of theta x plus 1 minus theta y, right? So we have to prove that this is greater than equal to this, right? But yeah, so is this in that form, right? So what is this? F of theta and u is ax plus b plus 1 minus theta, v is ay plus b. So what is this? Like, no, what are we trying to get here from here, right? So this is like a of this plus b, right? So what we want to get is a times of this plus b, right? So can we put this in this form? It seems like we can put this in this form, right? So so this is f of theta ax plus theta b plus 1 minus theta ay plus 1 minus theta b. Okay, so plus theta b and minus theta b gets cancelled, so 1b remains, and theta of ax is there, so we can take a common. A of theta x plus 1 minus theta y and plus 1b was left, and this is nothing but g of x plus 1 minus theta y, right? So we have proved that G is convex. This implies G is convex. Okay, so we have proved that the affine transformation of the space doesn't change. So composition of functions. Okay, so we can talk about when composition of a function is convex. Okay, so one so let us see this in the case where, let us say, k is 1, okay, and yeah, so let us say the case where k is 1 and h is going from r to r and g is going from rn to r. Okay, so in that case, what will be f, right? So g is going from rn to r and h is going from r to r. So what will be h of g? H of g will go from where to where, right? So h of g will go from, this is h after g, right? So this will go from rn to r, okay, which is f. H of g is defined to be f. So now the question is, for a composition of a function, what are the criteria when we can claim that this is convex, right? So is there any criteria using which we can actually claim that f is convex, depending on some properties given to us for h and g, right? So to do this, we differentiate, because we want to use, let us say we want to use second derivative test for convexity. So we want to know whether f, which is composition of two function, is convex or not. So we'll take the double derivative, and if we take the double derivative, then this is what we will get. Okay, if we take the double derivative of this, why we will get this? So the first derivative of f of x is what? This is the chain rule, right? Because it's the composition of the function, so this is the chain rule. So this is like a derivative of h with respect to g. So this will be h prime of g of x times the derivative of g with respect to x. Okay, so if I write this one more step, so this is like d by dg of h times dg by dx. This is the chain rule, and h is seen as a function of g here. So this in short form, we write this as h prime of g of x and then g prime of x. And then if we do the double derivative, then we have like product rule as well as the chain rule. So we can use the product rule, right? So let us say this is the first function and this is the second function, right? So the first function into derivative of the second, right? So the first function derivative of the second, so this will become this plus second function into derivative of the first. So derivative of this function will be h double prime of g of x and then derivative of gx again. So there are two g prime x, so you will get a squared of this and then h double prime of x. So this term you will get, and then this term is this term. Okay, so now given that this is given to us, now what are the criteria which will make this positive, right? And then this we can claim that it's convex. So the first thing is like f is convex if h is convex and non-decreasing and g is convex. So how do you convince yourself that with this given criteria on h and g, this will guarantee that f double prime is positive, okay, or greater than equal to 0. So why it should ensure greater than equal to 0? Let us see. H is convex. Since H is convex, what does it imply? So what does this imply? What I can conclude from here?
Dash x greater than 0. Greater than equal to 0.
H double dash is greater than 0. Greater than or equal to 0. Okay. And H is non-decreasing. What does this imply?
H dash x is greater than 0.
H dash is greater than 0. Okay. And non-decreasing, so it's like greater than or equal to 0. It could be constant also. Yeah. And what does this imply? Again, by the same logic, right? So this will be like second derivative. We will suggest g prime is greater than or equal to 0. So with this criteria, let us put these ideas here. H prime, so this term is greater than equal to 0. Now this term being a square is anyway greater than equal to 0. H prime being non-decreasing, so this is greater than equal to 0, and g double prime is greater than equal to 0. So whole thing is greater than or equal to 0. Right, so this is guaranteed when it to be greater than equal to 0, but there could be like other possibilities. There are case by case basis. So this is also another case where you can ensure that f double prime is greater than. So let us see, H is convex. So this implies, as you said, H double prime is greater than equal to 0. It is non-increasing. So what does this imply now? H prime is less than or equal to 0 now. Okay, less than or equal to 0. Okay, and g is concave. What does this imply? G double prime. So in convex, g double prime is greater than or equal to 0. In concave, g double prime is less than or equal to 0. Now let us see that with this, whether this will ensure f double prime x is greater than 0, right? So h double prime is greater than or equal to 0. This guy is greater than or equal to 0. This guy is always greater than or equal to 0. H prime is less than or equal to 0. So this guy is less than or equal to 0. And this guy is also less than or equal to 0. Okay, so the product of two less than or equal to 0 is this implies greater than or equal to 0. Okay, so product of two terms which are less than or equal to 0 implies greater than or equal to 0, right? So this overall, this is greater than or equal to 0, and overall this is greater than or equal to 0. So sum of two greater than or equal to 0 is greater than or equal to 0, right? So this is another criteria where you can claim. And similarly, other cases, f is concave. Now this is for the concave case. So now we are asking when f double prime x is like less than 0, right? So in the concave case, so h is concave, so h double prime is less than equal to 0, non-decreasing, so h prime is greater than equal to 0, g is concave, so g double prime is less than equal to 0. We plug in here, so this is like less than equal to 0, and this is like greater than equal to 0. This is greater than or equal to 0, and this is like less than equal to 0. So overall, 1 is less than equal to 0, 1 is greater than equal to 0. So overall this is less than equal to 0, and this is also overall this is less than equal to 0. So this is less than equal to 0. Okay, so this will imply again that f is concave. So these are criteria. So you see what is going on now, right? So there will be another case for concave, analogous case, and for n greater than 1, these ideas can be extended now. So now remember, we set n equals to 1, right? So this was like the scalar case we saw. So we put n equals to 1 and k equals to 1. Oh, okay. So I think previously I did not mention this correctly, right? So k is equal to 1. So h was r to r in the previous case, okay? And n was, so this was g was also r to r. Okay, so h of g was also r to r. So that was the case that we saw here, okay, where you can take this this derivative and you get only real value and so on. The problem is, like, if you go for n greater than 1, then you start getting gradient, which are vectors, right? So now the question is, like, how you can extend these ideas to general cases, okay, where n is greater than 1. Okay, so if n is greater than 1, then what is, so I think k is still kept to be 1, if I'm not wrong, because nothing is being said here. So I believe k is still kept to be 1. K has to be 1, I believe. Yes. Okay. So the second case is like k equals to 1 and n is greater than 1. So we will keep n to be just n. So in this case, what is the criteria now? H is from r to the 1. So this is like just r to r. And g is from rn to r and rn to r. Okay. So now it is just any arbitrary n. And in this case, then f, which is defined to be h after g. So h after g, so g is from rn and then to r, and then r is taken by h to r again. So this will finally, it goes to r. So we are talking about functions of this from rn to r, multivariate, single valued function, real valued function. Okay, so these are the, and for this case, these ideas, what I'm trying to say is, like, these ideas now can be extended. Okay, it can be extended to like to multivariate function. So if h is convex and yeah, here h tilde is the extended value function of h. Okay, so extended functions we have defined previously. Okay, we just add everything from the domain, okay, as infinity, okay, without changing the convexity and concavity or whatever. So so these are the extended results now. Okay, so I don't have much time now. I think 2 minutes maybe. So f is convex if h is, like, everything is just copy paste here, because everything holds actually. Okay, it's copy pasted here. So if f is convex, then h is convex, and so h is convex. H was from r to r, right? So h was from r to r. So h convex implies what? H double prime. So this is still real valued. So h double prime will be greater than or equal to 0. That's because of the convexity. Now h tilde is non-decreasing. Okay, so h tilde is non-decreasing. This means that the derivative will be positive again. Okay, because so this, assuming the derivative holds, right? I'm always assuming the derivative holds. So this will be greater than 0, and g is convex. Now remember that g is from rn to r, right? Yeah, so g is from rn to r, and we are saying that g is convex. So if g is convex, we are saying then we will have grad square of g here, right? So we will have a grad square of g here, and by convexity we mean that this will be like a positive definite. Okay, so actually what we have to do is that we have to like rewrite this in the form in the multidimensional case. We have to rewrite a correct form of this, right? Because in this is the formula for the real case. So what we will do in the next class, like now it's already 26. So what I will do in the next class is that I will write a, we need to change these things. Okay. Because so f is yeah, so f is a multidimensional, right? So this will be like grad square f here. So this will be like matrices now. So we have to rewrite this in a correct form before we make an argument for these things. Okay, but they will be an extent, they are analogous. Okay, that's what I'm trying to say. So we have to prove that this Hessian is positive definite, provided that like Hessian of h, I mean, for the h it's real valued, so Hessian is just a single number. This is positive scalar, and then this is like non-decreasing. Okay, so like the gradient is in this case the gradients are like positive, and then Hessian is positive definite. So I have to write the expression, then we can argue about this. So we can do this in the next class. So we are almost done with the convexity, I believe. So the slides. So there is something called conjugate function. That's the last part of the convexity. So I will define conjugate function in the next class. Why do I need conjugate function? Because I will discuss something called duality. Okay. So these are like dual functions, and that duality appears when you solve constraint problems. Okay. So you have to go to the dual space and then so on. So there will be the duality. So we will find dual functions of these. Okay, dual of these, and this will be used later on. So we will leave this here and then we prove all this, and then we will end the convexity with this chapter. Okay, this may be the most heaviest chapter in the first half, I would say, that you may have seen, the most heaviest maths or whatever you may have seen. There will be some maths needed in the dual that we will discuss, but we will discuss that much later. Okay, and then in the next class we will go ahead and start writing the models now. Okay, what are the types of optimization problems? What are the standard terms, minimizations, equality constraint? What are the like terms, keywords in optimization problem? Okay, what is called objective? What is called inequality? What is equality constraints? What is an unconstrained problem? What is a feasible set? Okay, and so on. What is infeasible set? And so on. What is optimality? What is called optimal? And so on. What is optimal value? Okay, so we will discuss now. We are already into now optimization models in some sense, but we will not discuss any application right now. I will just discuss models first, abstract models. Okay, just f denotes something. Okay, we will see later what it could be. So these are the things we are planning. Okay, so there are a lot of exciting things to come actually. So let us we are now getting into algorithms basically, and then applications, some selected applications. So that's the